A very warm welcome to this meeting. I'm Wilfred Otten, Professor of Soil Biophysics at Cranfield University and past President of the British Society of Soil Science. Today is the first in a new series that we've started, Zoom into Soil events, which will focus on nutrient efficiency. Before I welcome our two speakers, I would like to invite our incoming President, Bruce Lascelles, to provide a brief introduction to the host of our meeting, the British Society of Soil Science.
Thanks, Wilfred, and welcome again to everyone who's joined. It's really good to see a count of 95 people have joined the meeting so far. Many of you will be members of the British Society of Soil Science, but some of you won't be. So just as a sort of a brief introduction, the British Society of Soil Science is an established international membership organisation and it's a charity as well. And it's committed to the study of soil in its widest aspects. And we really are trying to reach out to as many people who are involved with or rely on soils in some way. And we bring together those working within academia as well as practitioners across soil science. And we've got about over 800 members currently within the society, both in private and public sector institutions, which includes academia, conservation charities, construction companies, as well as consultancies as well. And one of our aims is to raise awareness of soil science. And I'm really delighted that we've got this new series of events, and this one, the first one, Zoom into Soil, has already received, as I said, that fantastic response. So thank you again for everyone who's attended, and I'll hand back now to Wilfred.
Okay, thank you, Bruce. So before we begin, just some basic housekeeping. As there are so many of you here today, at the moment it's already over 100 that have connected, but more than 200 expressed their interest to connect. All your microphones have been muted. We will be taking questions at the end of both presentations, and my colleague Dan Evans will ask these to the presenters on your behalf. So there's a tab for you to submit your written questions anonymously if you wish, and although there is a raise your hand button, we won't be using that for this question session, only if the presenter asks you to show your hands. So after that, I would like to introduce our first presenter, Richard Reeves. Richard will be delivering a short talk for us on managing soil nutrients during changing weather patterns. Richard Reeves, from the farm perspective, will set out the importance and role of managing soil nutrients, placing particular emphasis on recycled nutrients such as sludge cake and green waste, and the significant impact the way this waste is treated prior to application can have. Richard will discuss the Met Office records that he has been keeping over many decades, the patterns emerging, and how these are impacting soils and the application of nutrients. Richard is a first-generation farmer. Since 1981, he has farmed 800 acres of land in Cheshire, using a wide combination of crops on a range of different tenancies. Prior to this, in the 1970s, Richard was involved in farm management with Imperial Chemical Industries and worked closely with the Duke of Westminster. Richard obtained a BSc in agriculture from Leeds University, and in the last 15 years, he has kept a close affiliation with Lancaster University, hosting students' visits to his farm. He has also been visiting speaker for environmental science students, talking on a range of topics, including UK farming practices. Richard is a former chairman of the National Farmers Union Northwest Crops Board and was a spokesman on organic resources. Richard, over to you.
Okay, thank you very much. Good afternoon, everybody. I do feel desperately underqualified to speak at such a august meeting, but get my best shot. As you say, I'm speaking today really due to my past, well, and current association with Lancaster Uni, going back probably 10, 12 years. When I was Crops Board chairman in the Northwest, we got to hear about research going on at Lancaster. I went to a number of meetings up there to interact with the staff, especially at the NDOD, and following on from that, we've going back a number of years, we've had student visits, firstly the environmental science students, and latterly the soil science master's students have come down to the farm, not just to look at the soil, but to get an insight into farming, because we're very aware a lot of students, if they're not from a farming background, they've probably never been onto a farm, let alone never spoken to a farmer. And we think it's very important that some of these guys will be decision makers in the future. It's very important that they've at least come onto a farm and spoken at ground level. And then in the last couple of years, Dan's come down and asked me or arm twisted me to say a few words today. I don't want to repeat what's been said. Yeah, I farm about 800 acres not far from Manchester Airport, a range of soil types and a range of tenancy agreements. No succession. My son is a farm manager in Suffolk, and this is influencing with nobody to take over the farm now. We're just on lifetime agreements. In fact, the main farm where I am is within Tatton Park, which is National Trust property. And when I decide to leave or give up a lot of that land, we'll revert back to the parkland. This is National Trust policy. They don't see the importance of food production. So it's influencing my decisions a bit as I look to wind down or find a way out of farming. The soils vary from a light sandy loam to a sandy clay loam. We're in quite a high rainfall area, certainly for arable farming. We average about 860 mil. That varies from a low of 620 to the last 12 months, March to March this year, recorded 1,250 mil. One of the problems, it's not just the high rainfall, it's obviously then the lack of drying days, and it's how that rainfall is spread. We can match yields, we like to think, with the best of operators for winter barley, probably spring crops, oilseed rape and oats. But we struggle, or certainly I do, to match the yields for winter wheat. And I put it down to too much rain, or the rainfall and lack of sun through the months of June, July and August, which was evident, certainly evident last year, and it looks like being evident this year when a lot of producers had nearly record yields. Ours were very disappointing, and we recorded June, July, August last year, just looking back, 390 mil for those 3 months. And this year, since the 1st of June, we've recorded 200 mil. So I think this is all impacting certainly on the wheat, on the quality, and yield. With farming in a traditional way, I'm well aware of the advantages for soil structure, etc., of min-till. But I think with the climate we've got, with the size of farm, I don't feel confident operating 2 systems. We have potatoes in the rotation, and often I feel that needs to be ploughed. Also, when we haven't applied sludgecake for what, 4 or 5 years, but when we did, that I felt needed to be ploughed. We also have a block of land where we put turkey manure on, and that certainly needs to be ploughed to get rid of the odour. So we just use a plough combination drill, a one-pass system, and the cropping's made up of winter wheat, oilseed rape, winter barley, oats. All our crops go to local markets. So that's basically the farm. I got involved with sludge cake going back to about the year 2000. That sludge cake coming out of United Utilities. And we applied it regularly for about 15 years. At the start, it was certainly, especially in the Northwest, I think the United Utilities were very late in the game. It wasn't a very scientifically applied product. Through partly my work with the NFU, we got them together, treating it and supplying much better analysis. And so for 12 or 15 years, we applied it quite regularly up till 4 or 5 years ago. I stopped using it then because of problems. A, we had increased our soil phosphate levels to levels which I thought would be sustainable for a few years. We're all reading 3s now or above. We were having problems with it being applied with contractors. At the start, we had some very good contractors, a very even spread, but as time went on, I got very unhappy with the standard of contracting. So very variable spread patterns. Also, we got into a run of 1 or 2 wet years where we would stockpile the material in the summer. It came to the autumn. It was then a question of weighing up the soil structure damage as opposed to the good that the nutrients were doing. The other thing is we farm in a semi-urban environment, certainly within Tabham Park, which is a very highly visited park. So problems with traffic going through, carting sludge cake, also now like blocks of land near houses, etc. So I decided, weighing up all those factors, although I could see the benefits, decided to give myself a break and also to reduce the hassle factor, if you like. We were set to start using it again last year. In fact, United Utilities soil sampled the whole farm. We were on stream to start taking it last June, but then the wet weather set in and we postponed it. And we need to think if we're going to go down that route again. So it's a question certainly for product like sludge cake in the Northwest. Yeah, it is fairly readily available because we farm near high centre of population, but it's a case of factoring that against soil damage and, say, the other negative factors. As far as other organic resources, a few years ago we did do some trial work applying green waste. And the green waste on soils like ours will complement the sludge cake very well because obviously the green waste is high in potash, so it will compensate sludge cake. And of course, with both those projects, we've got the extra nitrogen. But again, we've got the economics that didn't start to stack up. I felt we were having to pay too much for it. And again, we've got soil damage problems. Going forward on organic resources, yes, I was a big advocate, and in fact, I spoke at a number of meetings, partly on behalf of the NFU and the invitation of United Utilities. I still am a big advocate in the right situations. Going on to weather patterns, I've been keeping rainfall records for the Met Office for what, 30 odd years now. I'm not sure if overall we're seeing a huge difference in total rainfalls if we average them out, but I think we're seeing a much bigger variation and a seasonal variation. And as I alluded to earlier, I think one of our problems is we seem to be getting into a situation of higher, especially early summer rainfall, which, and because of that lower light intensities, and it just seems to me that that's affecting certainly grain quality with the wheat. It doesn't seem to be affecting the quality so much of other crops. And I thought at one stage it was just the way I was farming. I wasn't treating these crops properly. But then I thought, well, if we're getting decent yields, last year we were up to in tons an acre 3.7 on the barley. Well, that was the average yield, 3.8 on the rape, about 3 tons a month. So I thought, if we're getting quite respectable yields on those crops, why are we only getting 3 tons an acre on the wheat? The only thing I could put it down to was this lack of sun in the summer and the summer rainfall. And if I look back the years where we've had good summers, or summers that are more applicable to the main grain growing areas, yes, we can get the yields then. So going forward on that, yeah, I don't know the answer. Maybe we should be thinking about changing our cropping a bit. I did see reports pretty recently saying long term, is crop production going to move from the east to the west because of the lack of rainfall in the east? And certainly when I talk to my son in Suffolk, it's as though we're farming in 2 totally different countries. When they're full on irrigating there, we just sucked our ankles in water here. So as far as I suppose I haven't really touched as much as I should on the phosphates and organic resources. I think that there is going to be, certainly the Irish utilities have changed the way they're operating now. In the early days, they were actually paying us to take the sludge cake and paying us to plough, whereas now, all right, it's for free, but all the other costs are on us. So it's a factor of weighing up using these organic resources, I think, to our own particular farms, and to see how it fits in. So I think that's probably about where I'm up to. So yeah, I think probably leave it there and take questions if and when they come. Yeah, and just on the slides now are just Ian Dodd, myself, and Dan's in 1 or 2 of the students digging soil profiles and explaining soil structure problems or not, soil routing to the students. I say, we feel it's very important that we keep up this interaction, certainly on-farm interaction with these students who haven't necessarily been on an on-farm situation. Okay, thank you.
Okay, Richard, thank you very much for this presentation and your views about how the resources are used on the farm, and also your interactions with students, which is very welcome. We will be taking questions for both speakers at the end of today's session, just as a reminder. So we will move on to our next speaker, which is Dr. Martin Blackwell. Martin is a senior researcher at Rothamsted Research and is a soil biochemist with over 25 years of experience of studying both phosphorus and nitrogen cycling. Recent work has focused on phosphate use efficiency and cycling in arable and grassland systems, the role of organic phosphate in plant nutrition, and the development of better phosphate fertilizer application rate recommendations. Martin's presentation, Caught Between a Rock and a Hard Place, How Can We Use Phosphorus Fertilizers More Efficiently, will discuss the finite rock phosphate resources and the risk which the threat of this dwindling resource brings. Protecting future food production. Martin will discuss the fundamental changes which need to be made to the way phosphorus fertilizers are sourced to maintain food supplies for a growing global population. Over to you, Martin.
Let's see, can people see this? I'm hoping you can see that now.
Yeah.
You can see the screen. I can't, which makes it interesting. I'm going to need to be able to see this, so I'm going to have to. Right, is that okay? Can you still see it?
Yes.
Okay. Great. So hello everyone. Sorry about that. Another system to learn. I think I'm up to my sixth sort of Zoom type platform at the moment, and this is my first go on this one today. So apologies for that. But hello everyone, and thanks to BSSS for the opportunity to talk to you today about some of the issues surrounding the use of phosphate fertilizers, which I think is one of the most important issues related to soils that we face today. And as Wilfred said, I'm a senior research scientist at Rothamsted Research, and I've been focusing on nutrient-related issues in agriculture and the wider environment for over 25 years now. And I'm going to try and give you an overview of some of the wider phosphorus-related issues, and then focus on some of the more practical things we can do to address them. But I'm going to start with just a very brief history lesson. I'll try to anyway, if I can get this to move on. There we go. So the first commercial phosphate fertilizer was produced by John Bennett Laws in 1842, and you can see him there on the right of your screen. He realized that 1% of animals is phosphorus, but 80% of that phosphorus occurs in bones. So he dissolved animal bones in sulfuric acid and made the world's first superphosphate fertilizer. And this actually represented the start of the inorganic fertilizer industry. And you can see on the right there what he called his chemical manures as well, because he was well aware that putting manure on the land provided phosphate, but this was seen as being a more efficient way of doing it. And that actually represented the foundation of Rothamsted Research. He wanted to prove that these compounds he developed actually did have a benefit. So he set up the long-term experiments and founded Rothamsted Research. Some of you may have seen the long-term experiments in our Harpenden site. So there are many key issues associated with the use of phosphorus globally, and perhaps the most significant one is that global food production relies on the use of phosphorus fertilizers. Without them, we wouldn't be able to feed the world today or in the future. And today, most of the world's phosphate fertilizers are produced from rock phosphate, which is a finite resource, and coupled with the fact that the phosphorus cycle is largely linear and not circular, means we're using up these phosphate reserves. Now, the figure on the left here shows how phosphorus moves in a linear fashion from rock phosphate reserves through the fertilizer and food system, and is lost to surface waters where it causes big pollution problems by eutrophication. And what we need is a more circular system, such as that shown on the right here, where instead of letting the phosphorus that has originated from rock phosphorus deposits end up in the seas and oceans, we recover it and recycle it through the food system, much like the sludge cake, for example, that Richard was talking about earlier. But because of this linearity, it means we're losing the phosphorus into rivers and oceans and using up what is actually a finite resource. So from the title of my talk, the rock is obviously rock phosphate, and the hard place we're currently in is how we can use it more efficiently. Now, this figure shows the distribution of rock phosphate deposits in the world, and you can see the vast majority of them occur in Morocco, with only a relatively few other countries having significant deposits. And also note here that the UK has none, so we are completely reliant on imports for phosphate fertilizer. So I've said these deposits are finite, but how long will they actually last? Well, it's a rather complex and somewhat controversial topic, but using available data, it is possible to make some estimates of how long we can carry on as we are today. So this table shows the countries that have significant rock phosphate deposits, their recent rates of mining in the second column, and their estimated reserves, and with a simple calculation, if they continue to mine at that rate, how many years worth of supplies they have left. So the three largest producers are China, Morocco, and the USA, and they represent 70% of global production. Morocco and Western Sahara, the largest producers by far, have the largest reserves by far. I seem to have lost connection to the screen, sorry. There we go. China's the largest producer. They have no exports, and they have 23 years. If they carry on mining at the current rate, their reserves will run out in 23 years. India has a massive population, growing demand, and limited reserves, basically 29 years of supplies left. And the United States has 37 years of supplies left at current rates of mining. So there are some other major reserves, but many of them have geopolitical issues, meaning that it's not always going to be easy to access them. So for example, Syria, we know the issues that are going on there. There's not a lot of mining going on there at the moment. And also Russia as well, which I'll come back to later. So the world total is, currently we have 260 years of supplies remaining, which may sound like a lot, but bearing in mind that when I did this calculation 3 years ago, there was actually 300 years of supplies left. So the figure changes quite rapidly. If it carries on declining at that rate, we'll soon be using it up, and demand is likely to increase. So we need to use and recycle phosphorus much more efficiently than we currently are. Now, there are also some other imminent issues. One of the main ones being cadmium. High levels of cadmium consumption can cause kidney and bone disease, and sedimentary rock phosphate deposits tend to have quite high concentrations of cadmium, an average of around 32 milligrams per kilogram of cadmium. Interestingly, the igneous rock phosphate has low cadmium content, and that is what the main supplies in Russia are. So their phosphate is likely to be in high demand in the future, but there are often difficulties trading with Russia, as I think everyone probably knows. Now, because of the problems that it's known that cadmium can cause, there are new EU regulations to reduce the permissible concentration in rock phosphate, and they were agreed in 2018, and it's thought that they will actually come into force in 2022. So the new limit is going to be 60 milligrams per kilogram, which basically will affect around 8% of the rock phosphate supplies we have. Then in 4 years' time after that, they're going to be reduced to 40 milligrams. That's going to affect 31%. And then in 60 years, it's going to be reduced further to 20 milligrams per kilogram. And I don't actually know how much that's going to affect, but it's going to be a large proportion. So what people are going to have to do is they're going to have to process it, remove it, or dilute it down by mixing it with rock phosphate that has less cadmium in it. And all of that is going to increase costs. So that's another concern. Now, back in 2009, a group of scientists led by Johan Rockström assessed that some of the ecosystem services or cycles on the planet, looking at the safe operating space for things such as biodiversity loss and the nitrogen cycle and climate change. And as you can see, those three were deemed to have exceeded their planetary boundary. Phosphorus wasn't considered to be such an issue. It was thought that it was being used within the planetary boundaries. But then one of the authors in 2015, Stefan, did a different review, and he came up with this, and you can see now that phosphorus is considered to be as disrupted and as important an issue as the nitrogen cycle, as biological diversity, and probably even more so than climate change, because we can't actually do too much about it. At the moment, the phosphorus that's been released into the environment is there. Climate change, people are still hopeful that we can do something about it, but this was 2015, bear that in mind. So there are lots of key issues surrounding phosphate fertilizers and the way we use them. One of the main ones being only a small amount of fertilizer P that we add to soils actually remains plant available, and typically only 10 to 25% of what we add is taken up by the crop. Now, what often happens as well is people add extra P, it's over applied to ensure an adequate supply for optimum growth, a sort of safety net, if you like. But what happens then is P just accumulates in the soil and becomes fixed in as inorganic P and also organic P. But what can happen as well, if you look at the graph in the middle there, you get an increase in the available P as well, which is what the farmers are generally trying to achieve, but it reaches a certain point at about 60 milligrams per kilogram of Olsen P when you suddenly start to get a rapid increase in the amount of leaching. This is what we call the change point. And that causes eutrophication, as well as with nitrogen as well, obviously. It also represents the fact that we're losing it from the system. It represents inefficiency. So what can we do? Well, there are quite a few things we can do in terms of management of phosphorus fertilizers. You can tackle them through either the plant, the soil, or the fertilizer. There are other ways as well, but these are perhaps some of the most things that we're interested in agricultural research. So for example, with plants, we can look at root architecture. So plants aren't exploiting the same proportions of the soil depending on where they put their roots. We can look at root exudates, which can actually help release some of the phosphorus that's bound in the soil. And we can look at apportionment in plants, whereas, for example, some plants can use what are called galactolipids instead of phospholipids. So their requirement for phosphorus is much lower. In the soil, we can look at microbes, and there's a lot of work being done on phosphorus solubilizing bacteria. We can also consider mycorrhizal relationships, which can help plants get phosphorus that they wouldn't be able to otherwise. And also a fairly simple one is pH, getting the right soil pH as well. And then with regard to fertilizer, we can look at application rates. I think there's a lot of guidance around there, but there's still a lot of improvements to be made. And there are techniques such as placement, just putting the phosphorus where it's actually needed. And also with regard to fertilizer, you can look at different formulations as well. That's another key area that can affect its availability. So I'm just going to expand on three of these, one from each of the plant, soil, and fertilizer here, just looking at in a bit more detail. So firstly, we'll look at root exudates. So I mentioned that a lot of phosphorus is stored in the soil, and it becomes stored in organic and inorganic forms as well. This varies greatly around the world, and there is a general trend that in countries where large amounts of inorganic peat fertilizer is applied, inorganic forms dominate. You can see that there. But in countries, in some countries, organic peat actually dominates the forms in soil, and of particular interest is the fact that in countries that often have difficulty in accessing phosphorus fertilizers, so for example, the African countries here, soil P is dominated by organic forms. Now, can we utilize this soil P, these stores of soil P? Well, there are two main problems. Firstly, most P is tightly bound in soils and so inaccessible to plants. And even if it was accessible, organic P is generally considered to be unavailable to plants. They can't take it up directly. But plants have certain types of root exudates. They can release organic acids, for example, which can increase quantities of dissolved organic and inorganic phosphorus in soils. And some plants can release phosphatase enzymes, which can hydrolyze organic P to mineral forms, so it can be taken up. And there's some really clever plants like white lupin can actually do both of this, so they can they're really good plants for utilizing soil organic P. So we did an experiment to try and look at how this all works and what's the best combination to put plants in. And so we used plants with different root exudate properties, and so they either had single traits or they had two different traits. So that was either the citrate exudation or phytase exudation or co-exudation of both. So we grew them as monocultures for single trait species, intercrop species, or cross trait species as well. So those are the ones with the co-exudation. All intercropped and cross trait treatments had higher P accumulation than the monocultures. And in the graph at the bottom there, this is a graph of land equivalent ratio, which is a little bit complex to explain, but basically if anything goes above that dotted line, it means it's growing better, it's got higher yield, or in this case it's got a higher shoot phosphorus concentration than the monocultures. And what we found was that all intercropped and cross trait treatments had higher phosphorus accumulation in the monocultures. Shoot phosphorus accumulation was about 9 to 16% greater in the cross treatments than the intercrop treatments. That was despite actually the fact that those plants did exude lower phytase and citrate exudation. But the key point here is that co-exudation is more efficient for phosphorus uptake for both inorganic and organic P. So moving on to the soil pH, this is a fairly simple one really. Phosphorus gets fixed in the soil mainly by iron, aluminium and calcium, and you can see from the graph there on the left hand side it shows the amount of phosphorus fixation in the soil, and along the bottom we've got pH. So you can see that there are these valleys, as we call them, at two different pHs, two distinct pHs. One is around 4.5 and the other one is around 6.5 to 7 pH. So if pH is anything other than those, a lot of the phosphorus will be fixed, it won't be available. If we reduced it to 4.5, not everything would grow in a pH at that low, so the optimum pH level that we're looking for most plants in most soils is pH 6.5 to 7. And it's one of the things that's probably most neglected in agriculture today, but it's pretty easy to resolve. You can add lime to increase the pH, or you can add sulfur to decrease the pH. So a fairly simple win there, I think, and something that we could probably pay a lot more attention to. So if we look at application rate recommendations, Richard mentioned about phosphorus index as well, and that's what we use to do this. So in England and Wales, the recommendations are based on RB209 fertilizer manual, which is produced by AHDB now. It used to be DEFRA. So it's a two-stage process. The first thing you have to do is measure the available phosphate using an Olsen P method and refer to P index. You can also use a resin method. And then you have to take the crop into consideration, and then you can work out, looking at these tables, how much phosphorus you need to add. So if you've got an index, on the table on the left there shows the different concentrations for to give you a different index, and on the right there it tells you, if depending on what status your soil is at and what crop you're looking at, you can then add the correct amount of fertilizer. But there are a few issues with this. One is that Olsen P was developed for alkaline soils, and there's been a lot of debate as to whether it's the best measure of soil available P. Probably not in acidic soils, which when we're talking about grasslands, most of our soils, a lot of them are acidic. Also, soil types are not considered. Certainly in England and Wales, actually in Scotland, they're a bit more advanced. They do consider soil types to some extent. And then there's also this other confusion for the researchers and the scientists, is that the units that are used are milligrams per litre, whereas we always work in milligrams per kilogram of dry soil. So we're not always talking about quite the same language when we're looking at this subject. But the other question is, how are these things developed? How do we know what to add? So it's typically done through a critical P test. And what you do is you take a soil that has a 0 P index, you incrementally add different amounts of phosphorus, and you get a range of growth rates, which you can see at the top there for some grass. And then what you say is, okay, so we get to a point where if I keep on adding phosphorus, I'll get little incremental increases, but it's not going to be economic to do it. So typically we take either 90 or 95% of the maximum yield, and we call that status in the soil, that amount of phosphorus that we've added, we call that the critical level. So that's how we calculate it. It takes a long time, but there's been lots of experiments done around the country, in the field, in the lab, and they've come up with the results that they've got in the tables I showed you just now. Trouble is, it varies greatly due to soil type, in particular particle size, chemistry, and soil structure. Also, if plant crop and type affects it, and also the climate can affect it. So each year, you're not necessarily going to get it right, but I think the biggest issue is soil type and not addressing that. Now, we did some experiments to investigate this. We took 10 different soil types. We had 12 levels of the application rates, and we looked at 2 crops, grass and wheat. And you can see in the graph below there, the critical p-value is up on the left on the y-axis, and on the x-axis we've got just the different soil types. The green represents grass, the brown represents wheat. So you can see there's great variation for some of them. There's sometimes great variation for the different crop types. And basically what this is saying is I think we need to get better measurements, soil specific recommendations basically, and grow the right crop on the right soil. You can see for some of those, wheat grows really well, grass doesn't. In some it's the other way around. The grass grows really well, but wheat doesn't. So soil is really important for these recommendations. So just to summarize all those points, we can utilize organic P. Many soils contain relatively large quantities of organic P, and there are some plants that can access that P. It's not completely unavailable as we previously considered. But we need to consider how these traits are included in plants, and we know that co-activation is more effective than intercropping, but that's not always as simple to get a plant to do that. And also, I think we do need to consider the implications for soil organic matter. If we're going to be mining organic P, or we're going to be mining other forms of organic material in the soil. Optimized soil pH, liming is required in many soils. That's a fairly easy win. And also, I think we do need to develop crop and soil specific recommendations. So more critical P tests are needed. But we need multiple approaches. We need to consider plant, soil, and fertilizer management. And with that, I'll leave it. There's a lot of people contributed to the work that I've talked about there. So I'd just like to acknowledge all of their input. Okay, thank you.
Okay, Martin, thank you very much. As we said at the start, we will take questions from both talks. So Dan has been monitoring the questions you've been sending in. I hope he's got enough time yet, but Dan, would you like to ask the panelists some of the questions you have been receiving?
Thank you, Wilfred, and thank you, Martin, and thank you, Richard, for those inspiring talks there. So we have got a question here from Tom Powell, a couple of questions. The first is about the biosolids assurance scheme. This is a question to Richard specifically, but maybe Martin can come in as well. Has the introduction of the biosolids assurance scheme given you more confidence to use biosolids on your farm now?
Right, I think I got that. Biosolids assurance schemes, I'll be more confident about applying them.
That's the one.
Yeah, in the certainly my experience in the early days, there was very little information coming out of United Utilities regarding the composition of the biosolids. They were late in the game compared with other water boards. And so certainly in the early days, the assurance schemes, certainly for the likes of root crops and the monsters, didn't like biosolids. As time has gone on, the standard, if you like, of the biosolids has increased enormously, and the information, the analysis is much more forthcoming. But when going back a number of years, I certainly thought it was quite hypocritical that we were, as farmers, we were being encouraged to use organic resources as a way of doing our bit for the environment, because before that they were either going, these resources are either going to landfill or dumped out at sea or incinerated more and more. I thought it was quite hypocritical that then the maltsters and certainly the potato processors were anti. Now, I don't know what the situation is now. We grow potatoes or potato grow, I think, as potatoes on the or processing potatoes. They still don't like organic resources going on for that crop. That certainly needs a year between, and I think the same with the maltsters. But as far as our normal cereal or combinable crops assurance schemes, yeah, there doesn't seem to be a problem with that now, although in the early years, yes, there was. So, yeah, I hope that answered your question.
No, thank you, Richard. Maybe Martin can come in on there, but also maybe Martin, you could follow up on another part of Tom's question, which is there seems to be a lack of awareness as well about biosolids in agriculture generally. How can water companies, Tom says, make farmers aware of the potential benefits of biosolids? And perhaps I'd extend to that, how can soil scientists work with water companies to make them more aware of the potential benefit of biosolids and encourage them to close the nutrient loop and help them capture and recycle these nutrients?
So with regard to recovering nutrients, biosolids is one approach, but there's a lot of technologies moving on all the time at the moment, and there's a lot of recovery of these important nutrients taking place so that they're not released into our rivers. Iron phosphate is being used, for example, and there was a webinar last week, or workshop last week, that was quite extensive and giving mixed reports about actually using the iron phosphate that's been used to recover phosphorus from sewage works on land. And some people said it works really well, some people said it doesn't work at all. So there's mixed reviews. With regard to biosolids themselves, I think getting organic matter back into soil is crucial, so I'm not against that. But I think there's a lot of other alternative ways of recovering, in particular phosphorus, from sewage wastes and manures as well. And I think that will be the way to go, as well as finding ways to encourage people to get more biosolids onto the land and manures, because yeah, we've got to get more organic matter back into the soils.
Brilliant, thank you, Martin and Richard there for those answers. This is a very specific question to Martin. What were the crops used in the intercropping cross experiment that found greater phosphorus uptake for the mixed crop trial? We're talking about the types of crops used here.
Yeah, okay, I should have said that. They were actually tobacco plants. So they're genetically modified as well, I have to say, but it doesn't mean that some plants can't have these traits naturally. But these were the ones that we used for that experiment. Yeah, they were tobacco.
Brilliant, thank you. That was a very specific question. There's a question here for Richard, to bring Richard back in. There's one here from Juliet Brown. Richard talked about concerns regarding soil damage around sludge cake and green waste applications, so the damage to the soil. Can you explain on the possible soil damage here? Is it related to the physical application of both substances? That's from Julia Brown from Natural England.
Yes, it's partly with rainfall patterns. Whether it's going to be long term, I don't know. but one of the problems I've had is weighing up the advantages of applying sludgecake or other organic resources. I know for well the advantages, the improvement in soil structure, obviously the phosphate, nitrogen, some other trace elements. The negatives, though, in my situation here, and which is totally different to the main arable areas of the country, is the wheeling damage of heavy machinery, spreading the manure. We sell straw off. Most of the straw is ale because we're in a livestock area. But I'm questioning now, certainly after last year's experience, when it was very wet here, again, I'm questioning the economics of not just the straw, the nutrient value of removing the straw and having to replace that, but the soil structure damage of trailers, bales, etc. We're very careful when we're combining. We don't run alongside the combine, we just unload on the tracks or on the headlands. So we're very careful to minimise our own wheelings. But then when we're applying or have contractors to apply sludgecake or even straw contractors, it really grieves me when I see we're being so careful to minimise soil structure damage for these other machines going over, creating soil structure problems. So that's one thing actually on the field. The other problem we can have, certainly in a semi-urban environment where access to fields maybe isn't that great or as good as the broad acres of southern England or East Anglia, is damage to wagons coming in, tipping the sludgecake, damaging gateways, etc. And where we are neighbouring population, even though the cake now emits far less odour than it used to, it's still not a very pleasant material to have tipped in close proximity to habitation. So these are some of the factors which have made me shy away from it. Even though I'm a great advocate of the benefits, but if it can be applied evenly and without causing soil structure damage.
Thank you, Richard. And
so yeah, I hope that answers the question.
Yeah, thank you, Richard, and I apologise for the breakup if anyone experienced any breakup in the answer there. I think we got the take-home messages from Richard's answer, but apologies for the slight dodgy line. This is a question for Martin. You might see Martin's got a world map behind him. So this is about the availability of P in African soils. How does the aluminium and iron influence the phosphorus availability in our African soils? Can you throw more light on this? Is from Aoife.
Yeah, no, it's a really important point there, and we know that you can put lots and lots of phosphorus fertilizer onto some of the soils in Africa, and you don't see anything happen to your crop because it just immediately gets bound. You know, it's some of the oldest soils in the world, the most weathered soils in the world, and lots of iron and aluminium. So yeah, it is a problem. That's why trying to release that is one of the things we need to do, and I think, you know, plants with the right root exudates might be one of the answers there, but there's got to be phosphorus in the soil to start with. But it is one of the biggest issues that we get, is that you can apply lots of phosphorus fertilizer in some African soils, and see nothing for your money. So it's one of the problems we're tackling.
And just on that, Martin, is there and this is just a question also from Ben Butler, and we may also think about the different soil types around the world. Is there a tendency for phosphorus to leach from a given soil type, taken into account when calculating the application rates? Obviously, different soil types around the world, there must be a different rate or distribution of leaching.
There is to some extent, but interestingly, in the work that I presented there, they tried lots of different soil types, and what happens though is, depending on how much phosphorus you apply, you then get a different amount of available phosphorus, but that varies from soil to soil. So if you put the same amount of phosphorus on one soil type and then do the same on another, you can end up with very different amounts of available P. And so the point at which leaching occurs was always found to be around the 60 milligram per kilogram available P point. But it's actually, as I say, you can apply different amounts of phosphorus to different soils and you'll get different amounts of leaching from that point of view. The point at which it starts is pretty much the same. But yeah, soils will bind it differently. And this is why we need different recommendations for different soils. Some soils you can put phosphorus on and a lot of it will remain available. Other soils you can put phosphorus on and it's all bound up. So yeah, that's why the key thing is taking into account how phosphorus behaves in different soil types when you add it as fertilizer.
Got a couple of minutes left just for some final questions. Thank you for those who've entered them into the function here. Definitely more questions than we're going to have time for, I'm afraid, but I'm sure that Martin and Richard would be happy to talk at another event, I'm sure. So this one for Martin, which is kind of following on from the soil type here. This is from Lizzie. And what was the soil type number 2 in your critical P studies? Do you have any idea why you saw such a big difference in critical P levels between grass and arable?
So the soil types, there were 10 different soil types across a range of soils. 2 of them were alkaline, some of them were very acidic. They were gathered from grasslands and from arable land as well. So we tried to cover the whole range of soil types, and I think we did quite a good job with that, because you could see from the results that there was very little consistency across those soil types, which I think sort of strengthens the case for saying we need to get more specific soil-specific recommendations. Why there was differences between arable and grassland? Probably it's partly to do with pH on some occasions, although we did try and get that correct. It shouldn't have been any other limiting micronutrients, so yeah, it was a bit of a surprise to some extent that we saw that, and we need to look further into that. But I think it does show that I think it was more a case of arable doing better on grassland soils than the other way round, if you see what I mean, if that's where they were derived from, because arable crops quite like having a lot of organic matter there and good soil structure. That's what you tend to get with grassland soils. The other way around, some crops have been sort of developed to cope better with should we say poorer soil conditions. You know, they've been bred to do that, whereas grassland generally hasn't. So I think that could be some of it, but yeah, still something we need to look further into.
Fantastic, thank you, Martin. I make it 1 minute and 10 seconds towards 1 o'clock, so I don't want to keep you waiting. Thank you, Martin, and thank you, Richard, and thank you for all those questions. And I'll hand back now to Wilfred to close.
Thank you, Dan. So on behalf of the British Society of Soil Science, I would like to express our thanks to Richard and Martin for coming along to present today and taking the questions. They were both very interesting presentations, and we're sorry we can't address all the questions in the given time we have. Thanks also for attending this meeting. You will find a quick feedback survey when you leave the webinar, which we hope you will take at the time to complete. We'd like to hear about your feedback. This is the first one we organize, but our next webinar will take place on the 2nd of September at 12 noon, and keep looking at our social media feeds for further information, hopefully to follow shortly. Thank you and goodbye.